OCR A redox chemistry. Getting the most from Chemistry Explained means taking notes and completing tasks on paper or on a tablet, controlling the pace at which the lesson proceeds. Particularly when prompted, pause the lesson, complete the task, thinking it through, taking your time. When you're ready, return to the lesson and correct your work before proceeding. So redox chemistry relies on the idea of oxidation numbers, and there are rules for assigning oxidation numbers. We then apply the idea of oxidation numbers to writing and naming formulae, and then how changes in oxidation number are interpreted in terms of oxidation and reduction, that's redox, and then looking at redox reactions, how can they now be analysed using the ideas of oxidation number. So what is our idea of oxidation number? Well, in giving an oxidation number to an element in a compound, it is imagined that all compounds are ionic. So even covalent compounds are imagined to be ionic. And the oxidation number is the charge the atom would have if it were the ion. So looking at an example, let's take the covalent molecule hydrogen chloride, HCl. Now, if it were ionic, then the chloride ion would have a charge of 1-, and the hydrogen would be an ion with a charge of 1+, from our knowledge of ionic compounds, sodium chloride, etc. So we then apply this to the idea of oxidation number and say, well, the oxidation number of chlorine is -1 and the oxidation number of hydrogen is +1. So it's the same as the charge the atom would have if it were an ion in an ionic compound. Now, one thing to note here is that in an ionic charge, the sign comes after the number, whereas oxidation number, we signal that it's oxidation number by putting the sign, the negative, before the number. So it's +1 is the oxidation number, but 1+ would be an ion charge. Now, this is all much simpler than it might seem initially, because there are some straightforward rules to follow when assigning oxidation number. So, if we look at the first rule, all elements have an oxidation number of 0. That is a rule, an unbreakable rule. For example, the molecule hydrogen, H2, well, is it an element? Yes, it is. The oxidation number of hydrogen, therefore, is 0. Similarly, if a group 1 element is in a compound, so it's moved from being an element to forming a compound, then its oxidation number is always +1. For example, potassium oxide, K2O, the oxidation number of potassium is +1. Simply follows that rule. It is an unbreakable rule. Group 2 elements in their compounds are always +2 in oxidation state or number. So for example, calcium oxide, CaO, we know that the oxidation number of calcium is +2 because it's a group 2 element in a compound. Group 7, slightly more nuanced. Group 7 in a compound when the group 7 element is the more electronegative element. So we need to have ideas of electronegativity here just to help us through. But group 7 elements in a compound, when they are the more electronegative element, are always -1. So for instance, PF3, fluorine is more electronegative than phosphorus, and therefore the oxidation number of fluorine is -1. Please note, group 7 is not always -1 in oxidation number in its compounds, only when it is the more electronegative element. Hydrogen in a compound is always +1. For instance, in methane, CH4, each hydrogen has the oxidation number of +1. However, there is an exception to this. When hydrogens in combination with a metal from group 1 or group 2, these are higher up in the rule hierarchy, so we can't break group 1 always being +1, that has to always be the case. Group 2 is always +2, so hydrogen, if it's in combination, for instance, with magnesium, magnesium is always +2, hydrogen in a metal hydride is -1. So there's an exception to hydrogen always being +1 in its compounds. In a metal hydride, they are -1. Oxygen in a compound is always -2. So in carbon dioxide, we've got 2 oxygens. Each of the oxygens are in the oxidation state or have the oxidation number -2. There is an exception to the oxygen rule, and that is in a peroxide. For instance, hydrogen peroxide, H2O2, where the oxidation number of oxygen is -1. And then we have sometimes useful little add-on rule. Aluminium is in group 3, but it is always +3. That is not the case for other elements in group 3. So to make use of oxidation number, we need to have some rules to help us apply to compounds. And the first one is that oxidation numbers of all elements in neutral formulas sum to 0. So if we look at a neutral molecule, carbon dioxide, CO2, we know that oxygen follows the rule always -2. So 2 times oxygen will be 2 times -2. That comes to -4. The carbon, we don't know, we don't have a rule for carbon, so we don't know what the oxidation number of carbon is, but we know that all the oxidation numbers, when added together, come to 0. So that tells us that carbon must be in the oxidation state +4. Our second rule is a slight variation on the first, is in the case of a group ion, the overall ion charge is equal to the sum of the oxidation numbers. So rather than coming to 0, all the oxidation numbers in SO42- in the sulfate ion sum to -2. So let's just work through what that would mean. So oxygen, there's 4 oxygens. So that's 4 times -2, because oxygen is always -2, so that comes to -8. Sulfur we don't know, because there's not a rule, but we know that that must sum to -2. So that we deduce, therefore, that sulfur is in the oxidation state +6. And then the last rule is perhaps the easiest rule of them all, is the oxidation number of an ion is the same as the ion charge. So the magnesium 2+ ion, the oxidation number is +2. So the way to become familiar with oxidation number and assigning oxidation number, which is a very important idea in chemistry as you go through year 12 and year 13, is to apply it to some examples. So What I'd like you to do is to work your way through these problems assigning oxidation number for each element. So let's just do one here for you to show you what I mean, how you set it out. Well, sodium, if we try this one, sodium sulfide. Well, sodium, it's a rule, it's group 1 element, so it's always +1. But there are 2 sodiums There's only one sulfur, but they must sum to 0. So the sulfur must be, the oxidation number of the sulfur must be -2. So we apply the rule. Sodium is group 1 element, must be +1. There are 2 sodiums, so the total oxidation number due to the 2 sodiums must be +2. They are each +1. The sum of the oxidation numbers must be 0 because it's a neutral compound, and therefore sulfur is -2. Work your way down through each formula, working out the oxidation numbers for each element and list them in the boxes. There are in some cases 3 elements, so that's why there are 3 columns of boxes. Pause the lesson, work your way through, come back when you are ready to check your answers. So let's have a look at sulfur dioxide. Well, oxygen is -2, that is a rule. There are 2 oxygens, so it's going to come to -4. The sulfur must be +4 if the total is going to sum to 0. So sulfur +4. Hydrogen is always +1, couldn't be easier. Chlorine is the more electronegative element, so therefore chlorine is -1, summing to 0. Fe2+, well, that's a very simple rule. The iron has the oxidation number of +2. Now, hydrogen is always +1 in sulfuric acid. Oxygen is always -2. Those are rules. So we've got 2 times +1, that's +2. We've got 4 times -2, so that's -8. And then we've got sulfur. Well, sulfur must be +6 if all the oxidation numbers are going to sum to 0. +2, -8, +6 sums to 0. So sulfur is +6. Here sodium is in group 1. So sodium must be +1. Oxygen is always -2. Chlorine is not the more electronegative element. Oxygen is more electronegative than chlorine. So we've got sodium. Sodium at +1. We've got 4 times oxygen. That's going to be -8. 4 times oxygen is -8. So chlorine, if the sum of the oxidation numbers is going to be 0, chlorine must be +7. Yes, the oxidation of chlorine, the oxidation number of chlorine is +7. It's in group 7. It's only -1 where it is the more or most electronegative element. In this case, to make the oxidation numbers sum to 0, sodium at +1, 4 oxygens come to 4 times -2 is -8. Chlorine must be +7. Here, which is the more electronegative element? Well, chlorine is the more electronegative element, so it will be -1, which means that iodine must be, in this case, +1. Here, the oxidation numbers sum to -1. Oxygen's -2, that's a rule. Hydrogen is +1, that is a rule. So plus 1 and minus 2 do sum to the ion charge, which is minus 1. The sulfate ion, well, oxygen's always minus 2. So sulfur and 4 times oxygen. So 4 times oxygen is going to be minus 8. So the oxidation number of sulfur, plus minus 8 must come to minus 2. So clearly sulfur in this case is plus 6. So if we look just at sulfur here as an example, the oxidation number of sulfur in sulfur dioxide is plus 4. In the sulfate ion, it's plus 6. There is no rule about the oxidation number of sulfur. Then finally, if we look at the nitrate ion, well, oxygen's always minus 2. So 3 times minus 2 is minus 6. And nitrogen must be plus 5 if it's going to sum to minus 1. So nitrogen must be plus 5. 3 times minus 2 is minus 6, plus 5 equals minus 1. The oxidation numbers must sum to minus 1. So having introduced oxidation number, we're going to see how it's applied to writing and naming formulae. So oxidation number may be included in the name, and if it is included, it uses a Roman numeral. So for example, iron 2 chloride. The Roman numeral 2 applies to iron, so we know the oxidation number of iron is plus 2. We don't need to attribute an oxidation number to the chlorine because we can see, applying the rules, that it is the more electronegative element and therefore always minus 1. In other words, it's chloride ion. If we contrast that with FeCl3, well, here we've got iron 3 chloride. The oxidation number of iron is plus 3. So we can think of this as ionic if we like, Fe3 plus and 3 chloride ions, each at 1 minus, so iron 3 chloride. Similarly, as we did on the previous slide, we assign the oxidation number 7 to chlorine in sodium chlorate. So you may not have come across the chlorate naming, so it's similar to sulfate, but this is chlorine combined with oxygen, so sodium chlorate. And then we need to identify the oxidation number of chlorine at 7. We don't need to do so for sodium because sodium is always plus 1. Oxygen is intimated by the ATE ending, but it's always minus 2. So the only oxidation number that we need to specify is in the name sodium chlorate is the oxidation number of chlorine, so sodium chlorate 7. Looking at those 4 examples, H2SO4, HSO3, HNO2, HNO3, pause the lesson and can you name each of those 4? Come back to compare to my answers when you are ready. Okay, so it is hydrogen sulfate, but we need to assign the oxidation number of the sulfur. Hydrogen's always plus 1, oxygen's always minus 2, but sulfur in this case is 6. So it's hydrogen sulfate 6. H2 H2SO3 is also hydrogen sulfate, but we distinguish it from H2SO4 because the oxidation number of sulfur is 4. So that's hydrogen sulfate 4 using Roman numerals. So if that isn't quite clear to you, that's IV is 4, VI is 6. HNO2 is hydrogen nitrate, that is, we've got hydrogen and then nitrogen combined with oxygen, so hydrogen nitrate, but we need the oxidation number of the nitrogen. So this is the oxidation number of nitrogen there is 3, so it's hydrogen nitrate 3. And if we contrast that with the last example, well, this is hydrogen nitrate, that's meant to be a V, hydrogen nitrate 5. So the oxidation number of sulfur needs to be indicated, 6. The oxidation number of sulfur is 4, of nitrogen 3, of nitrogen 5. The hydrogen is always +1, oxygen is always -2, so we don't need to indicate that in the name. You also need to work the other way around, that is, starting from the name, work to the correct formula. So pause the lesson, and can you write correct formulae for those 5 named compounds? Come back when you're ready to check your answers. Okay, so iron 2 oxide, FeO. Why is that? Well, Fe, iron 2, means it's +2. Oxygen is always -2, so a 1-to-1 ratio will result in the sum of all the oxidation numbers producing 0. So FeO. Nitrogen 4 oxide. Well, nitrogen, we're told, is +4. That's in the name. So we need 2 oxygens so that the formula, the oxidation numbers, sum to 0, NO2. Chromium 3 chloride. Well, chromium will be a +3 ion, so we need 3 chlorides to sum to 0. Hydrogen chlorate, so hydrogen is +1. Chlorine, we are told, is +3, so it's hydrogen chlorate 3. Must sum to 0, so how many oxygens? Well, we need 2 oxygens, so that the oxidation numbers sum to 0. So it's HClO2 as hydrogen chlorate 3. And iron 2 sulfate 6, so iron is going to be Fe +2. The sulfate 6, well, sulfur will be +6, which means we need 4 oxygens, each oxygen being -2, so 4 oxygens will come to -8, 4 oxygens will come to -8. Sulfur we know is +6, iron is 2, so that's written as a formula, FeSO4. So, having done some preliminary work on assigning oxidation numbers and applying them to names and formulae, we can now move on to analysing oxidation and reduction in terms of oxidation number change. Now, most A-level students will have met oxidation and reduction before embarking on A-level in terms of electron transfer. Oxidation is defined as the loss of electrons, reduction the gain of electrons. So you may have come across oil rig. Oxidation is loss, reduction is gain. So let's look at how that applies to a particular example. So we start with Fe2+ ions, reacting with chlorine, the reaction produces iron 3+ ions and 2 chloride ions. So we now need to analyse this in terms of oxidation number change. So let's look what happens to the iron. Well, Fe2+ changes into Fe3+. How would that happen? How could Fe2+ become Fe3+? Well, by losing an electron. So an iron 2+ ion loses an electron to form an iron 3+ ion. But there are 2 Fe2+ ions forming 2 Fe3+ ions. So we just need to balance that in that way. So that would be loss of electrons, so that's oxidation. If we now look at what happens to the chlorine, well, the chlorine starts off as neutral atoms within a molecule and becomes 2 negatively charged chloride ions. That occurs by each chlorine gaining an electron. And we know that gain of electrons is reduction. Reduction is gain. You may have come across at pre-A-level work, GCSE or whatever. So we would call these as oxidation half equation and this the reduction half equation. If we look again at this chemical change, we can see that Fe2+ increases its oxidation number to 3+. So 2+ becomes 3+. And we said on the previous slide that that was oxidation. So we've got a way of defining oxidation as an increase in oxidation number. So on the previous slide we established that iron 2+ going to iron 3+ was oxidation. That's a change from oxidation number +2 to +3. So oxidation is interpreted as an increase in oxidation number. Now, we can also therefore, in contrast, say, well, reduction must be a decrease in oxidation number. And we can see here that the change for chlorine was defined as reduction. Here, the oxidation number of an element is 0, of the iron here is -1. So yes, 0 to -1 is a reduction in oxidation number, a decrease in oxidation number, I should say, and that is fitting the definition of reduction. So we've got an important new way of describing oxidation and reduction. Oxidation is an increase in oxidation number, and a decrease in oxidation number can be thought of as reduction. So I'd like you to pause the lesson and write and identify redox half equations for the reaction between magnesium and the hydrogen ion released by an acid dissolved in water. So the reaction between magnesium and an acid. Pause the lesson and can you rewrite those as 2 redox half equations. Come back when you are ready to compare your answers. Okay, so let's have a look. Magnesium turned into magnesium 2+. So don't forget, the oxidation number of an element is always 0, and this is obviously +2. Now, previously I'd written -2 electrons here, but at A level we're probably going to discard that as a way of balancing the equation and rather put them over on this side as electrons being released. So there would be magnesium 0 to 2 plus, that's an increase in oxidation number, so that is oxidation. So that's an increase in oxidation number. If we look at the hydrogen, so hydrogen ions turn into hydrogen gas. Well, the oxidation number of a hydrogen ion is +1, and for hydrogen as an element is 0, so that's a decrease in oxidation number, so that is reduction. How would we balance that? Well, we could also put in 2 electrons on the left hand side there. Having defined oxidation and reduction in terms of oxidation number change, you now need to be able to look at a redox reaction and decide, well, what's been oxidized, what's been reduced, what are the oxidation number changes. So I'd like you now to try some of your own redox analysis. So identify the oxidation number changes and state what has been oxidized and what has been reduced, if anything, in the following 2 equations. Pause the lesson and come back when you're ready to compare your answers to mine. Okay, so if I look at equation number 1, aluminium as an element is 0, and in a compound it's +3. Bromine as an element on the left hand side is 0. In a compound where the halogen is the more electronegative element, they have the oxidation number -1. So aluminium has gone from 0 to +3, an increase in oxidation number, that is oxidation. Bromine, on the other hand, has gone from 0 to -1, so that is reduction. Looking at equation number 2, let's just remind you that the nitrate ion is a -1 ion, so that makes the oxidation state of lead +2 in lead nitrate, and in lead, the lead oxide formula, it's also +2, so that's lead 2 oxide. So there's no change for lead. However, nitrogen on the left hand side in the nitrate ion is +5, and in nitrogen dioxide is +4, so we can say that nitrogen is reduced. There's a decrease in the oxidation number of nitrogen. So that poses a bit of a problem. Where is the oxidation? For every reduction there must be an oxidation. Well, on the left hand side all the oxygens are at -2. On the right hand side, the product side, 2 of the oxygen atoms are at oxidation number 0. So 2 of the oxygen atoms have increased their oxidation number. That is oxidation. So if I give you 2 more problems, I'd like you to pause the lesson, analyse equation 3 and 4, and come back to compare your answers when you are ready. Okay, so let's have a look at equation 3. Well, the oxidation number of phosphorus on the left-hand side is +3, and if you work through it on the right-hand side, it's also +3. Oxygen's always -2, hydrogen's always +1, which tells us that that is not a redox reaction. There has been no change in the oxidation number of the phosphorus, and oxygen and hydrogen are remaining compounds, so they're fixed by the rule +1 and -2. So that is not a redox reaction. Let's look at equation 4. Easy to identify the oxidation state of silver at +1 and at 0. So silver has been reduced. There's a decrease in oxidation number. Arsenic starts off at, I beg your pardon, at -3 for arsenic. And over here, it is on the product side, it is +3. So arsenic has gone from -3 to +3. So arsenic has been oxidized. So a slightly different problem. Write and identify redox half equations for the reaction between calcium and hydrochloric acid according to the equation as written. So could you analyse that equation for oxidation number change and then represent that reaction in the form of two redox half equations? Pause the lesson, come back when you have thought it through and written your half equations. Okay, so let's see what I've pre-prepared. Calcium going to calcium 2 plus, well, that's going to be by losing 2 electrons. Nothing required there. And of course, hydrogen ions are going to change to hydrogen gas. Now, why have I not written, by gaining 2 electrons? Why have I not included anything about chlorine? Well, calcium goes from oxidation number 0 to oxidation number +2. Hydrogen goes from +1 and then as in the element 0. Chlorine in hydrogen chloride -1 and in calcium chloride -1. So chlorine does not undergo any change. The calcium undergoes a change and the hydrogen undergoes a change, but the chlorine does not undergo an oxidation number change, and therefore it's a spectator ion. It's not involved in the redox half equations. So just now to identify which is which. So calcium from oxidation number 0 to +2, that's an increase, so that's obviously oxidation, and hydrogen going from +1 to 0 is a decrease, so that is a reduction. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers, move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.